and introduce my friend and colleague from NCRA, Professor Yashwant Gupta, who is the Center Director of the National Center for Radio Astrophysics. Yashwant actually did his early bachelor's degree at IIT Kanpur, and then he went to the States where he did his MS and PhD, working on pulsars. He made studies of the interstellar medium, and just as you know, stars scintillate, but radio sources when they compact scintillate due to irregularities in the interplanetary medium or the interstellar medium. So he's made some very interesting studies as part of his PhD, which has continued as well. And he joined NCRA when I was also there in 1991, I think, when he joined. And he has his research interests are on pulsars, the interstellar medium, using pulsars as probes of the interstellar medium, and also radio astronomy, instrumentation, data analysis, imaging, and where he has made a lot of very fundamental and important contributions. He has overseen the upgradation of the GMRT from its legacy system to the upgraded GMRT that was done under his leadership at the National Center for Radio Astrophysics. And as we'll also hear from him, that India is a leading player in the construction of the square kilometer array, where the effort is led at NCRA by Yashwant, Yash and his colleagues. And he received numerous awards and recognitions, Fellowship of Academies, and then also the Shanti Bhatnagar Award, the prestigious award. And rather than go on for too long, I will sort of thank him for making the time to speak to us today. He's planning to actually come here, but because of back-to-back meetings, he could not do it, and he's doing it online. Thanks a lot, Yash. It's a pleasure to have you with us. And please feel free to interact students and ask questions whenever you feel like it. And we look forward to an interesting and stimulating lecture, starting from uGMRT, which is also a SKA prototype kind of instrument, which has been making far more sensitive images and yielding a lot of interesting results since the upgradation of the GMRT. And we look forward to hearing from you, Yash. Thanks a lot.
Yeah, okay. Thanks, Sykes. And it was, I would have really liked to come over, but I was just concluding the other meeting, which actually spilled over a few minutes after 4. And I have the next one starting at 5. So I'm sorry I couldn't come there in person to interact with all of you. But I hope that the lecture can still be interesting, and just feel free to ask questions, even if you want as we go along or at the end. So originally I wanted to talk only about the square kilometer array, but then just looking through the program, I realized that you really actually haven't had a talk which tells you what actually exists in the country before we talk about the mega projects. And so I thought I'll just cover a little bit about the GMRT, especially the upgraded GMRT, because that also naturally connects to what we do and to the square kilometer array. And it'll also help you to connect. I think you've probably had only 1 or 2 lectures on radio astronomy, so hopefully it'll help you to connect a bit better to something as large and awe-inspiring as the SKA. So I'll just start first with a little bit about the GMRT. So the GMRT is actually a fairly old facility. When I say old, I'm talking about 20 years or so. But it was conceived by our group, led by Professor Govind Swarup in the 1980s, and built during the 1990s and operational since 2001 as an international facility available for use by anybody in the world. And it works in the range of 100 megahertz to 1500 megahertz, which is a small part of the very wide radio frequency window that goes from about, from what you can see from the Earth is about 30 megahertz to about 300 gigahertz. And but in that range, it is one of the largest and most sensitive facilities in the world. It's located not too far from where we are. I don't know if you've had a chance to visit. I believe you've had a chance to visit, right? There was a visit to the GMRT a few days ago. And it's, as I said, it's built and operated by our National Center for Radio Astrophysics. And if you zoom in into the configuration of the GMRT, there are 30 antennas, each of 45-meter diameter. They are arranged in this rough Y-shaped structure. But there's a central core area of 1 kilometer by 1 kilometer, which has 12 of the dishes, and the remaining 18 are spread out in this Y-shaped structure, with the furthest distance a little bit over 14 kilometers. And I don't know if you had enough exposure to the techniques of radio astronomy, but this kind of a configuration allows you to synthesize an aperture as far as the angular resolution achieved is concerned, whose size is equal to the largest extent of the array. So by using antennas spread out like this, you can actually synthesize an antenna of about almost 30 kilometers in extent and get angular resolution corresponding to that. And in terms of the range of frequencies over which the GMRT works after the upgrade is this wide swath of frequency with individual bands which cover themselves of the order of 2 to 400 megahertz of frequency coverage in each band, and combined together giving a very wide frequency coverage. And the way the electronics is set up, both the radio frequency electronics and the optical fiber system and the digital electronics, is that you can process bandwidth of 400 megahertz from each of the 30 antennas and make images over that large bandwidth of radio frequencies, which really makes it a very powerful instrument. In addition to the fact that the large antennas, and 30 of them, give you a very large basic collecting area, which again is important to get high sensitivity. In addition to that, it was designed from day one to support two different modes, which are complementary to each other in terms of how they operate and also in terms of the kind of science that you can do with them. So the first one is the regular interferometry or aperture synthesis mode, which allows you to combine signals from a distributed set of antennas like this in order to synthesize a single dish of large diameter and be able to make images of some extended object with that resolution. The other mode, which works for very compact objects where the angular size is so small that you would not be able to see any detail even with a 30-kilometer size antenna, whereas on the other hand, their signal varies very rapidly in time and you would like to record the data as if it was coming from one large single antenna, which is the sum of all the antennas. And that is what is called the array mode, where you can add the signals from the antennas directly and use it for observations of pulsars and other fast transients. And so this combination of features makes it a very unique and powerful facility. And if you've been there, but if you Google, you can see images from Google View. And this is a view of the central 1 kilometer by 1 kilometer region where you can just about make out these individual antennas. You can, of course, zoom this, and these are three of the closest separation antennas. And you need all these different separations in order to get the best quality image when you reconstruct the image in the aperture synthesis mode. And this tells you that 45-meter size antenna is huge, and most of the sensitive electronics, which first picks up the reflected radio waves and converts them into electrical signals, sits right at the top, at the focus of the dish. And in order to reach there and work there, you need this special high lift platform or crane, which goes up to a height of 32 meters to reach up to there. The other thing you'll notice is that, which may worry you, is that this looks like an antenna which doesn't have anything to reflect the radio waves. It just looks like a skeletal structure, but actually there's a very fine mesh which is there, which acts like the reflecting surface, and it's shaped out to have a parabolic shape, which you can't make out here, but using a mesh makes the antennas very light and then very economical to build also, which was also one of the key features of the design and construction of the GMRT. This Google picture actually shows you the main central building, which again you would probably have visited, which brings together all the signals from the 30 antennas to a common place where all the processing is done. And there's one control room over here from where the operator, single person, can operate the entire observatory and run a complete observation. So this shows the frequency coverage of the upgraded GMRT, like I said, going from about 110 megahertz up to 1450 megahertz. And there are just small gaps in a couple of places, which are places where man-made radio transmissions are very strong, and it's difficult to observe in those frequency ranges. And so we leave them out from the range of frequencies that we cover. If you are interested in the electronics and or the techniques, and then just a very short slide showing the basic receiver configuration. And so at the focus of the antenna are the feeds, which convert the electromagnetic signal into electric voltage, and these cover 4 different bands, which go from just a bit below 120 megahertz up to 1450 megahertz. And these are on a rotating turret, so you can rotate that and bring the desired feed to the point at the dish at the focus to pick up the reflected signals. And these signals are very, very weak, and so they need a lot of amplification and a lot of processing. And so there's a lot of electronics right there at the top, which does the initial amplification and filtering of the signal. Then it is sent down from the top to the bottom of the antenna. There, after some more electronics, it is finally transmitted via an optical fiber transmission scheme, which modulates the voltage signal onto an optical fiber. It's transmitted to the receiver station, and there it's demodulated and converted back to electrical signal. And then it is further amplified and further shaped and filtered. And then finally it is digitized, and all the digital processing is done then to produce the 2 modes of operation that I described, the aperture synthesis mode and the array mode. And those signals are integrated over certain time durations and then recorded onto hard disks for the astronomer to take away and do further processing and get the final products, the images that they want. As I mentioned, that it's a facility that's international, and it's used by astronomers from all over the world since 2002 onwards. And after upgrade, which was finished around 2019, it was released as the upgraded GMRT in 2019. And as you can see here, that there are users from many, many countries that have been using the GMRT over the years, but with a good, healthy participation from astronomers from India itself. So it's a good mix and balance of people, and this allows for the best kind of science to be done. It's highly competitive. There are typically the time requested for observations by different proposals from astronomers from all over the world. It overshoots the time that's available by a factor of 2 or more, which means that there is a stiff competition, and only the best proposals get selected for being scheduled on the telescope. And what do the people do with the GMRT? There's a whole range of science that a facility like the GMRT can be used for. And it goes all the way from studying our sun to looking for planets around other nearby stars, which, as you know, is a very hot topic. And from there to various other kinds of studies, pulsars, which are exotic neutron stars, which again, I'm sure you would have heard about during the summer school by now, and many other objects in the galaxy, supernova remnants, microquasars, and so on. From there on to explosive events like gamma ray bursts and now fast radio bursts and many other such transients. And then one of the big strengths of the GMRT is to be able to study hydrogen in various ways, neutral hydrogen in our galaxy and other galaxies. And it's designed so that you can pick up redshifted neutral hydrogen to very large redshifts. The 110 megahertz allows you to go to very large redshifts and see the very early universe it's a very excellent probe for doing that. And then radio properties of all different kinds of galaxies, galaxy clusters. A lot of work has been done to study these and to detect radio galaxies at large distances, and also cosmology and the epoch of ionization studies have been done with the GMRT. And last but not the least, it's also been used to do all sky surveys. So one was done about now 12 years ago at 150 megahertz called the TFR GMRT Sky Survey, which surveyed the entire sky visible from the GMRT in a uniform manner to make like an atlas, which is excellent reference material for astronomers wanting to study different aspects of the universe and wanting information at that frequency. So overall, what this results is in many new interesting discoveries and more than 40 papers using data from GMRT published every year in the various international journals. And so if we ask what happens beyond the upgraded GMRT, so that's what brings us to the square kilometer array as the next big radio astronomy facility. And I will illustrate that with a plot of what is the sensitivity of the radio telescope as a function of radio frequency. And the sensitivity that the upgraded GMRT provides is shown in this curve here. And as you can see that the range is from about a bit over 100 megahertz to over 1 gigahertz. And in that frequency range, it is compatible or comparable with the best facilities at other frequencies. For example, the JVLA, which is a well-known radio telescope in the US. And if you ask what comes with the better or higher sensitivity, then it is the SKA1, phase one of the SKA. And that is what we will talk about as to what is the SKA and where we are going with that. So the SKA is actually it's one of these next generation global mega projects, and I think in the school you've already heard about some of the other mega projects that are happening in astronomy, and this one in particular probes the radio window, and the way the SKA is envisaged, the full SKA called which stands for 1 square kilometer of collecting area. So if you remember, the GMRT collecting area is about 30,000 square meters. And so 1 square kilometer would be about 30 times the GMRT collecting area, which would make it a very sensitive instrument. More importantly, it's not just 30 times sort of more antennas, but it's actually 3,000 antennas, which is significantly more, 100 times more. And that's because the antennas are smaller in size, which gives them a larger field of view, which makes it more interesting. And they are also spread out, or will be spread out over much larger distances, up to thousands of kilometers, to get much higher resolution than what the GMRT does. And the frequency range of coverage will also be much wider than what the GMRT does. So you're going a bit below the lower frequency limit of the GMRT and several times higher, up to 10 gigahertz compared to the 1.5 gigahertz for the GMRT. And SKA is going to be located in Australia and South Africa. And the reason for this is that today, if you ask what's the biggest challenge to radio astronomy, in fact, if you ask what's the biggest challenge to astronomy, it is all the man-made activity, whether it is light pollution or it is radio pollution or it is satellites going overhead and various things. And so we always want to go to regions where the man-made noise signal is the minimum. And so you have to go to semi-desert regions far away from human habitat. And so places in Australia and South Africa have been identified as the best places to locate the SKA. And the way it is designed, it will do cutting-edge science in all areas of astrophysics, and I'll show that in a moment. And it is, of course, many new kinds of technologies required in order to achieve this kind of very impressive parameters that we are talking about. Now, currently, what's happening is that phase one of this is being attempted, which is a bit more modest in terms of the scope, but still bigger and more sensitive than any other radio telescope available today. Therefore, it's still capable of doing transformational science, and I will talk about that in more detail in a moment. And the present status is that the design for the SKA Phase 1 has been completed. It was finished around 2020, and the construction phase was approved in late 2021 and started actually last year. And the construction work is now picking up steam and is expected to complete by around 2027 or so, with commissioning and early signs hopefully starting from 2026 onwards, and the facility to be fully operational by around 2028 to 2030. And so the SKA will take its place in this pantheon of all these large facilities, and I think some of these you've heard about in the summer school, where India is a partner. So you heard about LIGO India, you've heard about the TMT, where India is participating, and its SKA is the third one, where India is a partner in the facilities. And these are I mean, some of them you already know. JWST is already operational for last couple of years. Alma has been operational for last few years, and so on. And others are sort of coming online in the near future. And so the range of science from the SKA is really going to be very exciting and phenomenal. All the way from formation of first stars and galaxies in the very early universe. So we'll be able to probe that all the way to the current universe and many exciting things. But all the way beyond that to something which is just on the sort of on the other sort of fringe of astrophysics, which is searching for extraterrestrial intelligence and actually trying to look for signals coming from extraterrestrial intelligence. So that's a very vast spectrum of science, and it's one of the broadest range of science of any facility worldwide. And here are the details of that, which I will not go through each item, but except to indicate that all the way from the very early universe, cosmic dawn, to cosmology, dark energy, to the evolution of galaxies, to the origin and evolution of magnetism in the universe, to study the transient sources, of which we are finding more and more interesting ones, and then very specific kinds of physics, like testing strong field tests of gravity using pulsars and black holes. This is in terms of finding binary systems where you can have a binary system with a pulsar and a black hole, and also a detection of low frequency gravitational waves, which will be complementary to the detection of gravitational waves with the system like LIGO. And from there to the cradle of life is what the term is, but it includes various aspects of life, which is ranging from detecting complex molecules, which are the harbingers of life, to detection of protoplanetary disks around stars where the first planets would be forming, to actually trying to detect sort of signals generated by extraterrestrial intelligence and being transmitted. The last but not the least, whenever you build a facility which is many times more powerful than what exists today, it is likely to find unexpected results, new discoveries on topics that you did not think of when you build the facility. And that's what we call serendipitous science, that you find something new and interesting and completely unexpected because your ability to see the universe is now much better. And a lot is expected of that kind from a facility like the SKA. So the SKA actually is a distributed telescope. As you saw, any radio telescope is distributed, but the SKA is much more distributed in the sense that it is spread out over 3 different continents. The 2 parts of the antennas will be located in South Africa and Australia, and the actual administrative headquarters will be is in the UK, near Manchester at the historical Jodrell Bank Observatory site. So it's a fairly spread out global observatory. And we talked about the design phase, which was a lot of effort. It ran for 6 years from 2014 to 2020 to complete the design, and cost over 200 million euros of money to do this. And a large number of teams from different countries were working together, including those from India, which I'll talk about later on. And as I said, we are not attempting to build the full SKA in one go. What is being talked about now is phase one, and I'll show you what the specifications for phase one are in a moment. And that's what I talked about, the timeline for construction of phase one. And phase two would then be taken up after phase one is working reliably, and the results are coming out from there. That's when talk of phase two will start about how to build phase two. So phase one has restrictions in terms of the parameter space, and both the frequency coverage will be a bit less than the full SKA. The maximum distances to which antennas will be spread out will not yet reach the 1,000 kilometer, but it will be of the order of 100 kilometers. And but all of this work will be done keeping in mind that this will be expanded further to build the full SKA. And the sites, like I mentioned, I'll show you in a moment the more details. In Australia, for what is called the SKA low, and South Africa or SKA mid, and I'll explain that in a moment what is meant by SKA low and SKA mid, and the global headquarters in the UK. And I already talked about the design and the construction phase. As you can see, it's fairly big project in terms of when you talk about the money required to build something like this. And I'll come back to that as to how these large international collaborations then try to do this. So the SKA mid, it stands for the mid frequency, which is the higher part of the frequency range over which the SKA will work. Is going to be in South Africa, which will be about 200 antennas, 15-meter diameter each, spread out over 150-kilometer region, centered in this location here, which is in the northern part of the country of South Africa. And this is far away from a lot of the human habitation. And it's a radio quiet region protected by additional legislation which restricts what kind of man-made transmissions are allowed over there. And there's an existing facility there called the Meerkat, built by South Africa, which will be incorporated and merged with the SKA when it is fully ready. The SKA low, which is for the low frequency part, which will be from the 30 megahertz to about 300 megahertz, lower part of that frequency range the SKA will cover. It will be located in Western Australia, close to the edge of the Great Australian Desert. And this has a design which is somewhat different. It is not dish antennas, but it is actually dipole antennas. So the dipole is the most basic form of radio antenna. And at low frequencies, it's more advantageous to use dipoles in some situations. And so there will be stations consisting of many dipoles, like 512 dipoles together, and then 256 such stations. So you can think of each station as the equivalent of one dish antenna, but it is actually a bit more sophisticated and more flexible than a single dish antenna. And then there are the order of 100 such stations spread out over a 80-kilometer region. And this is, again, a very challenging aspect of building something like that. And the headquarters, which you can see a picture here, it's sort of the main buildings are ready and occupied and being used, is located at the historical Jodrell Observatory site, which is just a little bit south of the city of Manchester. And this is where the entire sort of administrative headquarters for the SKA project will be. And in order to deliver something like what we are talking about, the SKA will be using technologies which are really right at the cutting edge in terms of what can be done. And that ranges all the way from advanced and diversified design principles for how you build antennas. So as I already showed you an example that there are two different kinds of antenna designs for the SKA mid dishes, but even then the dishes are a bit different. So this is the artist's sort of illustration of what the SKA dish will look like. Now there are actually a few such dishes now built and available at the South Africa site. And as you can see, this again looks different from the GMRT dish, and it's different for various reasons. And again, part of the design is to optimize it to give the maximum performance for the kind of science that needs to be done. And then on the other hand are the dipole fields of dipole antennas for to be used in the SKA low in Australia. More importantly, a lot of this electronics will be cooled to very low temperatures because when you cool the electronics, especially the most sensitive electronics, which sits right at the focus of where the signal is first picked up, and you cool it to lower temperatures, then it gives you lower noise. And you always want to reduce the noise that the electronics is adding so that it corrupts the incoming signal as little as possible so that you can get the best signal to noise and the ability to detect fainter signals. And this again is a fairly sophisticated technology because you are now using cryogenics to cool the system down. And then finally, when you pick up the signal from each antenna, as I showed you in GMRT also, there's optical fiber which transmits the signals from the individual antennas to the central processing facility. This challenge here is much higher, not just because of the larger number of antennas or the larger number of dipole stations from which you're taking the signal, but also because of the larger bandwidth and many other factors which increase the total traffic. And so it'll reach better bits per second, which if you say, well, what does it mean? If you take the total internet traffic today around the whole globe, it'll be of that order when the amount of data that's flowing from the antennas. And I'll show you a little bit more of that in a moment. And then finally, you have to be able to analyze all this data coming. And in GMRT, we do it with a small, software-based system which uses GPUs. But when you scale it to the requirement of the SKA, you require almost supercomputing capabilities, petaflops of computing in order to process this data. And so there's all of that. And then finally, you have to, even when you do that, the volume of data that you generate in terms of the final images is still substantial, and you need to store all of that. And there's again a significant data storage challenge. And again, I'll talk about that in a moment. And finally, you have to manage this entire thing. The large array of distributed antennas with sophisticated electronics and the data flow and the computing, all of this has to be monitored, controlled, and run in a coordinated fashion so that the entire thing works as a coordinated observatory carrying out observations. And the way things work today is from the time you submit a proposal and the proposal is accepted, and then it has to be scheduled on the telescope, and the telescope has to carry out the observations, generate the data, which has to be analyzed, the images have to be produced. So all of this is a end-to-end processing and management of the observatory. And so very sophisticated systems need to be built to do this. And that's again a big challenge. And then finally, when you get this data to make sense out of it, to get the best results and the astrophysics out of it, it's very hard to do it the way it was traditionally done, which is the human mind or brain and eye looks at it and tries to decipher what one is learning. When you have such large volumes of data, large number of images with a huge number of pixels and so on, you have to go in for machine learning and other modern data analytics techniques in order to get the best results. And all of that is part of the toolkit that will be used in order to get the best results from the SKA. And already people are working on these kind of things with the existing observatories. And these are just numbers to drive home the points that I was making and also to summarize the things for the SKA1 and also for the future projection for SKA2. So SKA1 is actually being built now. And these are the kind of things in terms of the new dishes to be built in SKA mid and the number of low frequency dipoles to be built for SKA low, the data signal transport requirements in terms of, you can see terabits to petabits per second, and the computing signal processing requirement, and the software and the data storage requirements, and so on. So as you can see, these are all very challenging things, and some of them are things which are still not yet built and will get built. But first you have to build, of course, the electronics. And here's an example of the kind of frequency ranges. So I showed you the 4 frequency bands that the upgraded GMRT covers. And if you compare with that, you will see that these bands are broader and cover much larger frequency ranges with instantaneous bandwidths, which go up to gigahertz and even 2.5 gigahertz compared to the 400 megahertz that we do at the upgraded GMRT. And so all of this is fairly sophisticated radio frequency engineering coupled with the cryogenics that you need in order to cool the receiver down to low temperatures. And this just graphics illustrating the signal flow to just again give you a feel for how the data flow grows and the computing grows in order to handle the data. So when you look at the SKA low or the SKA mid from each of the dipole stations or from each of the dish, this is the rate at which data will be coming, 2 petabits per second and 9 terabits per second. And once you get it to the central station, you need of the order of 50 petaflops of computing in order to do the immediate real-time signal processing that is needed to reduce the data. And then once you've done that, you still have of the order of terabits per second of data coming out, and this has to be then sort of uh, process to get the science results, the images that have to be made, which, in the GMRT at this point, you record the data. And then you make the images offline. The astronomer takes away the data and does it. Here, this data volume is so high that it's not, and also the task of reducing and making images is fairly, will be complicated. So the SKA will make the initial images which will then be shared with the astronomers or the users via the regional centers located in different parts of the world. So this is where the data goes out of the observatories to other places in the world. And so at this point itself, you're generating very large volumes of data, which is now the final images or the final data products which the astronomer can start studying and using to do science or further processing if they want to extract more information. So as you can see, this itself is of the order of 300 petabytes per year, and that's a very large amount of storage. And so this data has to then be made available to astronomers from all over the world. And the concept is that different regions of the world and maybe individual countries could have what are called SKA regional centers, where you would keep some or all of the data from the SKA. Maybe you would keep the data which is most useful for astronomers from your country, which they are working on, and you would then develop the local data analysis pipelines to extract the final information from the data and be able to do the science that you want to do. And so finally, when you do want to do this, this data has to flow on the undersea cables that exist, which carry a lot of the regular communication from across the world. And so there's this work going on to see how you would use these in order to transfer the data from the SK mid site in South Africa and the SK low site in Australia via hubs located at specific locations where needed, and then transferring it to the main users, the main countries or the regions which are wanting to use the SKA data. And so that brings me to who are the main sort of users and countries and contributors. And so it's a large international collaboration with many countries involved. As of today, there are already about a dozen countries that have signed up and joined the current SKA council. And there are more that are interested and preparing to join the SKA. So it's an ongoing process to grow the community of countries that are part of the SKA. So with that, I move on to talk about what has been our role from India in the SKA and what are we planning. And so, uh, given our strength in radio astronomy, we have always been part of the SKA, right from the initial days when the first ideas or concepts for what that something like the SKA should be there, what it should look like when they were first mooted, more than 15 years ago now. We have been part of that. And then when formal work started in the preparatory SKA phase, India was one of the partners, and we led the concept design work for the SKA monitor control system, now called the Telescope Manager for SKA. And then in 2012, NCRA joined the SKA organization as an observer member. And in 2015, we transferred that to a full membership when the Department of Atomic Energy, representing the Government of India, joined the SKA organization. So this is all during the design phase of the SKA. This was for doing the design work for SKA. And and over the years, during the design phase, there's been significant activity and contribution from India. And these activities are coordinated by the SK India Consortium, and these activities are funded by the Department of Atomic Energy. Though going forward, the Indian participation in the SKA will be jointly funded by the DAE and the DST, the Department of Science and Technology. And I'll come to that in a moment. So the SK India Consortium is already has a large number of organizations ranging from astronomy research institutes to IITs to ISSAAs and universities, and even some of the colleges in India who are members of the SKIC. Set up in 2015, and today having more than 20 institutions as members. And each member has one representative in the SK India Council, and the council then decides and steers the overall activities of the SK India Consortium, which has two main sort of areas of work. The science related activities and the technical related activities, which are coordinated by two subcommittees. And the science activities focus around building up the science capabilities in the country, identifying the science interests which for SKA in India, and preparing the science community to be able to use the SKA when it's ready. And the technical aspects involve contributing to the design work and contributing to the construction work of the SKA, and contributing our knowledge and technical understanding, as well as gaining from the work done by other countries contributing to design and construction of the SKA. And so in the design phase, we played a significant role in the technical activities. We were involved in three of the design work packages: the telescope manager, the central signal processor, and the signal and data transport. And in the first one, we were the leader country with a consortium of um, uh, 6 other countries joining us to do the work. And this was also done in partnership with the software research groups and software industry in India. And so they were partners with us during the design phase of the SKA telescope manager. And the telescope manager is one of the critical systems that I was explaining earlier. It is like the brain and the nerve center, and it provides end-to-end monitor control for the entire observatory. And so it's complex software that is needed for the complete life cycle management from the time you submit the proposal to the time you get the final data delivered as a user. So this is just a graphic which tries to illustrate how the telescope manager is actually connected with each and every part of the observatory, including the human interaction aspects, as well as interacting with all the hardware and managing and running this. And this is something that we led in the design phase, and we are also actively involved in the construction phase and hoping to be one of the main contributors in the construction of the telescope manager, but working closely with industry in India so that we can get the best of the engineering skills to be used for doing this work. So this is when we completed the design phase, and it was approved by the international review panel that the SKA observatory set up for reviewing, which they do for any design work. And this was something that got a lot of attention back in 2018. And when we move from there to the, as I said, the construction phase has sort of started, and different countries' contribution to different parts of the telescope in the terms of work packages have been identified. And we have been identified as the lead country for work on the enhanced version of the telescope manager. The scope of the telescope manager has been increased to include some more functionality, and India has been identified as the largest contributor to that. Again, there will be partner countries from the SKAO partnership who will be joining with us for doing the work. And this work has sort of already started. And we are also processing work package with members from the SK India Consortium, Raman Research Institute, and others actively involved in this. And this will build some of the digital hardware which processes the signals coming from the individual dipoles in any one of the stations in the SKA and a lot of sophisticated digital signal processing over there. Also part of the design and construction of the one of the receiver packages of the SKA mid. So as I showed you, there are different frequency bands, and each requires a different set of receiving antenna and the electronics to be built. And we also have some role in this, that last part, which is called the science data processing. When you get the data from which you make the final images or the data ready products. And in this case, we are involved in some of the pulsar signal processing that will be happening. And overall, India's planned contribution adds up to about 6% or so of the construction cost of the SKA. And so in addition to contributing directly to the building of the SKA, our plans also include having a regional data center in India. So I explained the concept of the regional data centers, which will act as the repositories of the SKA data generated from the two locations in South Africa and Australia. And the plan is to have one of these data centers in India, which will house a good fraction of the data, especially the ones that is relevant for the science projects that teams from India are focusing on. And also plans to have significant human resource development program so that we can get train more people for both the science related as well as the technology related activities that are part of the SKA participation, and also develop a more sophisticated technology R&D program. So if, as I said, that SKA phase 1 will be followed by SKA phase 2. SKA phase 2 is likely to have a more advanced set of technologies that will be used because you're building something even more bigger and more ambitious. And our aim is to be able to do some of that R&D by ourselves in the country so that we can contribute when it comes time to work on SKA phase 2. So this proposal for Indian participation in SKA is currently in the final stages of review by the Government of India, and we are hoping to get the approval, which will be an approval for funding for 10 years of participation, carrying us up to a bit beyond 2030, which is the time frame by which the SKA is expected to be fully operational. So that then brings me to the summary, and I will leave the summary there for you to read, which highlights all the way from the upgraded GMRT to the current status in the SKA. And I'm happy to discuss and answer any questions that you may have. Okay, so I'll stop sharing so that I can see you all and you all can see me. And if there are any questions or discussions, we can go ahead with that.
You can just go ahead and ask that. Yes, can hear you. So maybe you have a question.
Yeah, Professor, can you tell us the International Treaty Organization, which you had in the last slide? Could you tell on that?
You want to know about the
International Treaty Organization.
Yeah, so I didn't go into the details of that. So when the SKA was set up for the design phase, it was set up as a not-for-profit organization registered in the UK, and it was the managing body, and the different countries that joined just had like a memorandum of agreement or understanding in order to work under that umbrella to do the design work. When it moved to the construction phase, it has transitioned into what is called an international treaty organization, and this is something which is much more formal. And you would have heard of other international treaties, and India is part of quite a few international treaties. They're often for different kinds of spheres of activity, but there are treaties even for coming together to work jointly in order to carry out large science projects. And so this is so there is a certain set of treaty documents which have been drawn up in jointly by the representatives from all the countries, and DAE officials from India were involved in the discussions to finalize. And so each member country that joins has to sign the treaty and adhere to the principles of the treaty. So it's like an agreement. And then there are well-defined principles by which activities take place, and well-defined guidelines how you can become a member, what are roles and responsibilities of a member, how you're expected to contribute, and so on. So that's what it refers to as an international treaty organization.
Can I ask you, sir, anybody using the facilities of SKA or GMRT and the results they get, have they to pay any charges?
So when a facility like the GMRT or the VLA that I mentioned in the USA, when these kind of facilities were built, and it has been a tradition in radio astronomy that you don't charge for the to any astronomer for using the facility and getting results from it. So it is the funding is done by the national funding agencies of different countries. In order to run the facility and to enable high quality science to be done by anybody in the world, and it's complementary, has been so. Now, when it comes to the big facility like SKA, where different countries are contributing to building the facility, things have been a bit different, and there has been the way it is going to work there is that if a country has contributed 10% to the cost of the SKA, the attempt will be that 10% of the time on the telescope will be time where the leading scientists will be from that country for that project. So that's the kind of understanding. So in some sense, you are paying now for the time that you are getting on the telescope to do science. So this is the difference between current national level facilities and the international facility like the SKA.
Thank you.
Any questions from the students? No? Everything's crystal clear. You're excited about this telescope. Jamir, is anybody on Zoom? Any questions in Zoom?
No questions like in Zoom.
Sir, I'm getting a question, if you allow me to ask. So the maintenance cost of all these facilities will have to be again shared by some funds created by the international treaty.
Yeah, you're right. So what will happen is once the construction phase is over, it will go into a running phase, and during the running phase, there are certain operational costs, which maintenance is one part of it. There are other operational costs, just the cost of the people who are there running it, cost of electricity, cost of all of that. And those operation costs are again to be shared between the member countries. And in the way the SKA treaty is set up, the members will have a share in that operation cost, which is in the same ratio as their share to in the construction cost.
Thank you.
Okay, there are no more questions. Thanks very much, Yash. Thanks a lot for making the time in spite of your back-to-back meetings.
Thank you. And I'm just in time to join my next meeting. Okay. Thanks, everybody. And, anybody has any questions, queries, just feel free to write an email or send a message anytime later on also.
Yeah. Okay, thanks a lot.
Okay, then. Thank you. And then bye.
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 Okay.
Recording stopped.
So we're done for the day? Yeah. See outside after a while.
Clear your storage. Clear cache and all. Okay. Happy. Okay. Oh.